Today we'll show you how to connect an unknown brushless motor to a controller. A brushless motor usually has wires that are color-coded. This one has 3-phase power wires that are yellow, blue, and green, and a Hall sensor cable that has 5 wires that are red, black, yellow, blue, and green. But what if you have a brushless motor that has wire colors that don't match with your controller? So over here I have a motor that came from a 40-volt brushless lawnmower. It has a 5-pin Hall sensor cable and a 3-phase power cable. The problem is it's not color-coded the same way as my controller. So in this video I will show you how to figure out all of these wires to connect a brushless motor to a controller. The very first thing you want to try is to plug it in without the Hall sensor. Some brushless motors would run just fine without a Hall sensor, even though it has a connection for a Hall sensor cable. Over here I have an e-bike that has a bad controller. This bike has a mid-drive brushless motor. The thing about mid-drive brushless motor is that it usually comes with a built-in controller. So if your controller is broken, you're out of luck. Or are you? They call it built-in, but actually you can remove it. So I already removed the controller. So as you can see, it has exposed wire, and judging by the dirtiness of this contraption, you can tell that it has been used like this, exposed the elements for a while. And yes, I've been using it for the last 10 years like this. Yes, that's 3,650 days without a Hall sensor, just fine with absolutely no problem at all. Here is the Hall sensor connector, and it's unplugged. The Hall sensor on my controller is also unplugged, and I can turn it on and it will run just fine. So here is the controller for this bike, and the Hall sensor cable is unplugged, and it's a 24-volt system. So I just plugged it in my 24-volt cobalt battery. Now I can turn it on and working. So with the current low, when it's not on the load, it's very low. And you can see the current when it's not under load is very low. It's only about 1.5 amp. So what I did was I just connected it to an aftermarket controller. The only wires I used was the 3-phase power cable. It's not color coded, so I just blindly connect them and switch them around until the wheels spin in the right direction with the lowest no load current. That means you also need an amp meter to test it. When you try to switch them around, make sure you keep one wire connected while switch the other 2 wires around. For example, if the first combination is yellow, blue, and green, you want to keep the first wire, which is yellow, connected while you switched the blue and green around. So the second combination should be yellow, green, and blue. Next, you can move the green wire to the front, and your third combination would be green, yellow, blue. Then you want to keep the green wire connected while you switch the yellow and blue. So the fourth combination would be green, blue, yellow. Next, you move blue to the front and do the same thing, and you get 2 more combinations. In total, you have a total of 6 ways to arrange the 3-phase wires. I can confirm this using some math. In mathematics, we call this 3 with an exclamation mark, or 3 factorial, because we have 3 elements that can be arranged in different ways. And 3 factorial would equal 3 times 2 times 1 equals 6. I cannot tell you which motor would run like this without a Hall sensor. You cannot tell by just looking at it, so you just have to try it. It only takes a few minutes to try all 6 combinations. The trick here is again an amp meter to make sure when you test it like this, it has to run at low current when it's not under load. The current would be around 2 amps. If when you test it and it runs fine and everything, but the current is 8 amp or more, that's not a good combination. Sometimes this combination gives you the best output of all 6 combinations. But because it has a high current load when it's not under load, imagine how much higher current would be when you put it under load. It would either burn your wires, your controller, or your motor if you put it under load. Furthermore, you're gonna waste a lot of power to heat. Instead of getting 20 miles of range, you might get 3 miles or so. So a good combination would run around 2 amps or less when it's not under load. The reason why I can run this motor without a Hall sensor is partly because my controller has a learning wire. This white wire is a learning wire. I just have to plug this wire in first before I plug in the 3-phase power wires. When you power it on, it should learn the position of the magnets and the coils and send power to 3-phase wires accordingly. So just plug in the white learning wire first and then try the 6 combinations of the 3-phase wires until you get the correct combination. And then after that, you have to unplug the learning wire for it to run correctly. However, most brushless motor with a Hall sensor cable would not run without a Hall sensor. So next, I'm going to show you how to connect this cobalt brushless motor to a controller. This is a little bit more complicated because you have to deal with both the 3-phase wires and the Hall sensor wires. Previously, you only have 3 wires to switch around and you already have 6 different combinations. Now you have a total of 8 wires to switch around, right? 3 wires for the phase, 5 wires for the Hall sensor, total of 8. There would be a gazillion different combinations to connect them together, right? Well, sure, if you want to try it blindly, and you might short out and burn the motor or the controller in the process. But I'm going to show you step by step to make it a lot more simple to figure out. And by the end of this video, you're gonna be a master of this, and it would take you less than 5 minutes to figure this out. So grab a drink, a pen and a piece of paper to take note, because this is going to be exciting. The very first thing you gotta do is to figure out the black and the red wires on the Hall sensor, and that's what I'm going to show you next. And in order to figure this out, we need to understand a little bit about Hall sensor cable. On a standard e-bike controller like this one, it usually has 5 small wires. Some have 6 wires. And usually the 6th wire is not very important. Usually it's a temperature sensor of some sort and it's not very important. You can actually omit it and just cut it off. The most important part is the 5 wires. Black wire is ground, red wire is positive 5 volts. The other 3 wires, blue, green and yellow, are the 3 Hall sensor wires that go directly to the motor. Inside the motor, there are 3 small Hall sensors on the stator. They will sense the position of the rotor, the magnets on the rotor, so that will tell the controller where to send the power correctly into the 3-phase power cable that goes back to the motor. So over here I have connected everything back together, just like the original lawnmower, including the original switch, and I can still run it from here. The only thing I did differently is this wire here, which is just an extension wire that goes from the Hall sensor, from the motor to the controller, and I have exposed wire which I can use my alligator clips so that I can connect to my testing equipment. The first wire to figure out, which is the easiest wire to figure out, is the ground wire, which is the black wire. And I'm going to use my meter here using the continuity test, and if the wire is continuous, it will beep. The ground wire on the Hall sensor cable shares the same ground wire on the whole system, which is also from the main battery. So I'm going to connect one end to the ground wire of the battery, which is the thick black wire here, and the other end I'm going to touch all of this wire. If any one of these beep, it will be ground for the Hall sensor wire. There we go, the second wire. Nothing for the rest of the wires. So the only wire that beeps is the second wire. And for this test, you don't have to turn on the system, just leave it off. Now that I know that this wire is ground, I'm using the black alligator clips so I can easily identify it. Next step is to find out the positive 5 volts. For that, I'm going to use my voltmeter here and measure the voltage when the system is running. Now I know that this is ground, so I'm going to connect this to the black probe on my meter, and the red probe I'm going to connect to the rest of the Hall sensor wires and determine the voltage, and I can tell the difference. Alright, let's turn on the motor. That's 5 volts. 2.4 volts. 2.4 and 2.4. So as you can see, the positive 5 volt is this wire here all the way to the right. And if you look at the original connector on the original motor, and that is the wire on the far right, which is gray. I was thinking that the positive 5 volt is this red wire here, but it's not at all as I predicted. Positive 5 volt is gray wire, and it's on the far right side. Now that I know the two wires, ground and positive 5 volts, I only have 3 wires left, right? The yellow, green and blue, but for that I can safely connect this motor to my e-bike controller to test it. So as you can see, we can easily figure out the ground and positive 5 volts using a multimeter. But in order to figure out the other 3 wires, which is yellow, green and blue for the Hall sensors, we are gonna have to use a different method, because you can see from my test, the voltage output when the motor is running of the 3 wires for the Hall sensor, they are all the same at 2.4 volts. So there's no way to figure out using a voltmeter. For the next step, I'm gonna have to move this motor out of this housing and connect it directly to my e-bike controller. But I can do it safely now, because now I know the ground and positive 5 volts. Now that we already figured out the red and black wires on the Hall sensor cable, we only have 3 wires left: yellow, green and blue on the Hall sensor. And as you can see from my previous test, the yellow, green and blue wires have the same voltage output at positive 2.4 volts, so it's okay to switch them around without worrying about shorting out anything. So the process is exactly the same as the previous process with the 3-phase wires I showed you earlier on my e-bike. Switch them around by keeping 1 wire connected and only switch 2 wires at a time. You will get a total of 6 different combinations. Now for the 3-phase wires of the motor, we're going to do exactly the same thing, and we will get another 6 different combinations. And because we have to pair the Hall sensor combination with the 3-phase wire combination, we have a total of 6 times 6 equals 36 different combinations. Now if you're curious to know how many different combinations if we didn't figure out the red and black wires on the Hall sensor, I have an answer for you. So 5 wires on the Hall sensor for a total of 5 factorial equals 5 times 4 times 3 times 2 times 1 equals 120. On the 3-phase wires, we have 6 combinations, right? So the total amount of combinations would have been 120 times 6 equals 720 different combinations. That's mind-boggling. You're going to have to spend the next 2 years to switch out wires to get the right combinations. Anyway, let's go back to our discussion. So we have a total of 6 times 6 equals 36 different combinations for pairing both the Hall sensor with the 3-phase power cable, right? But here's a secret. You don't have to do all 36 different combinations to find out the correct one. That's because for every combination of the Hall sensor cable, you have 6 combinations for the 3-phase cable, right? And 1 in 6 of those combinations is the right combination. And I'm going to prove that to you in a little bit, but first let's try and connect the first 6 combinations, and I'm going to show you what I mean. Right, so let me show you how to figure this out. Got my cobalt 40 volt motor connected to my controller. I've got my battery connected and ready. Got my amp meter to measure the current, and I got a printout here so I can take notes for this test. For the Hall sensor wires, we already know the red and black wires, right, from the previous test. The rest of the wires are unknown, so I just connect them together in any random order. It doesn't really matter at this point. So we got red, black, yellow, blue and green, which is here. For the connection to the phase wire, to make it less confusing, I'm I'm gonna label the wires for the phase that goes to the motor 1, 2, and 3. So 1 for black, 2 for yellow, and 3 for brown. And the wires with the alligator clips come from the controller. So I'm just gonna switch these wires around and keep the wires on the motor constant. So over here for my printout, for every Hall sensor combination, we have 6 different phase combinations. And this column here is for the phase wire for the motor. This column here is for the phase wires for the controller. So for the first combination, we got 1 to yellow, 2 to blue, 3 to green. Just like what we have here. Here we go. First combo. So the motor runs low and the current is very high, almost 8 amp. So I don't think this is the right combination. So here's my note for the first combo. Not only does it run low, it is also very loud. Moving on to the second combo, I'm going to keep the yellow and switch the other 2. So the yellow stays the same, and I'm going to switch around the other 2 wires, which is green and blue, like that. And while you're switching, do not turn off the system. So you can see here my switch here stays on. Just make sure you don't touch the wires. The reason why you have to keep this on while you're switching the wires around, because if you keep turning on and off while you switching the wires around, the system is gonna reset and you're gonna get a different result. So here we go, combo number 2. So as you can see, it only vibrates and the current is pretty high, over 10 amps. For the next combo, I'm gonna keep the green the same and switch around the other 2. And that's combo number 4. Here we go. Nice and smooth, and the current is low enough, around 2 amps. Here's the result for number 4, and I also noticed that it runs more quiet than the previous one. So I think this is the right combination. We'll see. So for the next combo, we're gonna keep the blue the same and then switch out the other 2. So blue stays the same. These 2 will be switched out. Here we go. So it vibrates only and the current is pretty high, over 10 amps, even though it's not even moving. And that's combo number 3. For the next combo, I'm gonna keep yellow the same and switch out the other 2. And that's combo number 5. Here we go. So as you can see, it runs faster than the previous one, but the current is very high. It's about 8 amps. Here's the result for number 5. I noticed that not only does it run fast, it is also loud and at high current. This is not under load and it's already 8 amp. Imagine what happens when you put it under load, right? It's going to be a lot more than 8 amp, and that's not very efficient. And a lot of power is going to be wasted as heat that goes to the wire. Heat will go to the motor and will go to your controller. So this is not a good combination. So for the last combination, I'm going to keep the green the same and switch the other 2 around. So we go, green the same, yellow and blue is gonna be switched around like so, and it vibrates only and the current is over 10 amps. So here's the result for combo number 6, and obviously it is not a good combo. So among the 6 combination, combo number 4 is the good one. Here's my final results for all 36 combo, and this was done on the hoverboard motor, not on the cobalt motor, but it doesn't really matter on what motor. The principles are all the same. So we got 6 pages. Each page is one Hall sensor combination, and for every Hall sensor combination we have 6 different combinations for the phase, and among the 6 combinations for the phase we have one correct combination. So the ones that I circle are the correct ones. So as you can see, for every page we have one single correct combinations. However, among the 6 correct combination they have here, okay, these 3 run clockwise and these 3 run counterclockwise. So let's say for the first 6 tries you have one correct combination and it runs clockwise, and your setup requires clockwise. So great, congratulations, you are done. But what if your setup requires counterclockwise? So what are you gonna do to switch from clockwise to counterclockwise without having to go through all of this all again? That's what I'm gonna talk about next. So let me show you how to switch out the correct combo from clockwise and counterclockwise and vice versa. So we're gonna have to go back to combo number 4 for our previous test, which is the correct combo and it runs clockwise. So let's say that your setup requires counterclockwise, and because for every Hall we have 6 phase combo and only one of the combo is correct. In order to find another correct combo, we are gonna need to have another Hall combo. That means you're gonna have to switch the Hall sensor first. Here's a wire for the Hall sensor. I'm just gonna keep one wire the same and switch the other 2 around. So let's say I'm gonna keep the yellow wire the same, and I'm gonna switch the other blue and green around, so like that. Put right back in. And remember, when you do this, only switch around the wire that comes from the controller, not from the motor. And here is the trick to find out the correct combo that runs counterclockwise. If we switch out the blue and green on the Hall, we're gonna have to keep either blue or the green the same on the phase. So here on the phase, we're gonna keep the green the same and switch these 2 wires around, or keep the blue the same and switch these 2 wires around. So the most we have to try is only 2 more times to find the right combo that runs counterclockwise, as opposed to if you don't know what you're doing, you have to try 30 more times, right? We have 6 more here already done, so you have 30 more times if you don't know what you're doing. So let's first try it with the green. So I'm going to keep the green wire the same and switch the yellow and blue around. Like so, and here we go. So it vibrates and very high current, over 10 amps, so it's not this combo. So let's put it back to its original position before we can switch it out again. Okay, that's the original position for the phase. Now we're gonna keep blue the same and switch green and yellow around. Like so. Here we go. That's it. That's the one. It runs nice and smooth. It runs counterclockwise and the current is low at 2 amps. So that's the right combo. So there you have it. To sum up, if you are extremely unlucky and you try the first 6 combo and the last one you got is this and it runs clockwise, but your setup requires counterclockwise, all you have to do is to try 2 more by switching 2 of the Hall cable and whatever the color that you choose on the hull, you keep the same on the face, and you only have 2 more combos to switch around for a total of 8. And that's why you don't have to do all 36 combo to get the right one. The maximum amount of combo, if you're extremely unlucky, is only 8, and it's gonna take me only about 3 minutes or less to do 8 combos. So there you have it. It's extremely easy, and it only takes a few minutes to figure this out. Once you know what you're doing, it's gonna be an impossible task if you just blindly switch around 5 Hall sensors and 3 phase for a total of 720 combinations. That's just ridiculous. And also, the other Hall sensor, you got the 5 volt and the ground. And if you just blindly switch around the 5 volts, you're gonna short out this wire here, so you're gonna either burn your motor or your controller. I know this is a long video, but I just wanted to cover everything that is needed to get this done successfully. Any questions, just write down below, and I will see you next time.